So now let us consider the formation of the complex nickel tetracarbonyl. So tetracarbonyl, as I told you already, C capital O you have to write. You should not make it small. If you make it small, it is cobalt. So nickel tetracarbonyl, you have to remember carbon monoxide is a neutral ligand. So nickel here is in the zero oxidation state. That is in the, it is not losing any electron during this compound formation, complex formation, right? So you have to take nickel in the normal electronic configuration of nickel. Ground state configuration. What is the ground state configuration of nickel?
4s2 3d8.
4s2 3d8. See, normally in textbooks, they will write the 3D before 4s. Though the filling order of 3D is after 4s, position-wise, we see that it belongs to the inner shell. So it is usually written before 4s. So 3d8. Right? Now, during the formation of complex, we need some hybridization to happen. Equal energy orbital should be ready for the ligand to fill its electrons. Now, we know that carbon monoxide again is a strong ligand. Okay. But now let us see what happens during the formation of complex. Now, the 4s, see in the previous case and all, when we saw the formation of this one, the 4s orbital, since nickel was in the 2+ state, the 4s orbital was vacant, right? So the ligand could force pair the electrons in the 3D and create one d orbital for hybridization. Vacant d orbital that could be involved in hybridization was provided. But here in this case, the 4s electrons are as it is. So even when the ligand tries to force pair the electrons, it can only force these electrons to pair up with the electron. One of these electrons in the 4s, one gets paired up with this, another one gets paired up with this. So the 4s alone can be made vacant and not the 3D. So in this case, though CO is a strong ligand, force pairing of electrons does not produce a vacant d orbital, because the 4s orbitals electrons are only force paired. Okay, so this is a case, this is an anomaly in which though the ligand is strong, we are able to produce only a tetrahedral complex. Therefore, this complex can undergo, since there are no vacant d orbitals available, it cannot undergo dsp2 hybridization. See, 4 coordinate case, we have two types of hybridization. If it is dsp2 square planar structure, if it is sp3 tetrahedral structure. So here d orbital involvement in hybridization is ruled out. So it can undergo
3d orbital. We'll be having vacant d orbital will be there, ma'am. 4d.
See, when there are p orbitals available, 3 p orbitals are free, no? Okay.
Yes, ma'am.
See, only during force pairing, if one of the d orbitals in the 3D is available, so energy wise, what will you see? Hybridization, what is the concept? Almost equal energy orbitals will only involve in hybridization. So yes, P3, D. So energy wise, when you see 4s, 4p, 4d. See, you are having 3p orbitals of equal energy available for hybridization. But 4d is slightly greater in energy than 4p. So it will go only for these three. Okay. So sp3 after if if p orbital is not available here, then it will go for the higher energy option. But in the dsp2 hybridization case, the 3d orbital is of lower energy when compared to 4p. What is the energy order? 4s, then 3d, then 4p, no. So d orbital is of lower energy than 4p. So it will take one s, definitely it will take one d if it is available, 3d because it is of lower energy. Then 4, so after taking these two, only 2 more it needs. So it will take just 2 from the 4p. But in this case, when it is involving valence shell orbitals for hybridization, when 3p orbitals are equal energy of equal energy are available, it will take those alone. It won't go for D. Okay. So here is sp3 hybridization. Valence shell 4 coordinate case hybridization ஆகும்போது 3p orbitals are available. 4s and 3p only will be taken. Only from inner shell, if it is taking, it will take one of the d orbitals if it is available for hybridization. So when it takes one d orbital for hybridization, it will take only 2 from the p, giving ds equal energy dsp2 hybrid orbitals. dsp2 involves 3d, 4s and 4p, 2 4p orbitals only. And sp3 involves s and 3p orbitals of the 4s, 1 4s and 3 4p orbitals of the valence shell only. So here sp3 hybridization, it will give rise to only tetrahedral complex. So this is a case in which a strong ligand forms a tetrahedral complex. This is the only example we have in all our discussions in this chapter. Only this example, we see that though the ligand is strong, we end up in a tetrahedral complex. Then again, but magnetic property also, there is an anomaly here. See, normally we see that most of the tetrahedral complexes are paramagnetic. But here, this is because of the presence of, yes, because of the presence of a strong ligand, which forces all the electrons to pair. Even when it forces the electrons to pair, it is not able to produce a square planar complex. We get only a tetrahedral complex. And this is a case in which the complex shape is tetrahedral, but it is spin paired complex. All the spins are paired up. And it is a magnetic property wise, it is not attracted by the magnet. So it is a diamagnetic complex. Clear?